In this module, we're going to review the concept of linearity. So linearity has two basic properties that must be satisfied in order for a system to be called linear. The first is the additive property, and this is demonstrated with this slide here, where imagine we have some input image I sub 1 as a function of x and y. It goes into a system that takes the input image I, and let's call this function is called R, and it returns an output image k sub 1. Now assume we take another input I sub 2, pass it through the same system, and get an output k sub 2. If the additive property is satisfied, then if I come with an input I1 plus I2, if the system satisfies the additive property, then the output will be K1 plus K2. So it is simply if I put in a sum of inputs, the output must be the sum of the outputs I would have gotten from the individual inputs. The second property is the scaling requirement, and in this case, once again, I have I1 giving me K1, and now I multiply I1 by a scalar, so this is represented by A sub 1 here. And if the system satisfies the scaling property, then essentially the output must just be a scaled version of the original output. So in this case, it's A1 times K1. So to summarize, a system is linear if for any two inputs, I1 and I2, that have outputs K1 and K2, then the response, the weighted sum of the inputs, is just simply the weighted sum of the outputs. So in this case, the weighted sum is A1 times I1 plus A2 sub I2. That's the weighted sum of inputs. And the weighted sum of outputs is A1 times K1 plus A2 times K2. So here are some examples to consider. And we wanted to see if these systems are linear. So in the first system, the input is G and the output is G plus 10. So the question is that linear? The second system, the input is G and the output is 10 times G, and the question is that linear? And finally, the third example is the input is G and the output is simply Gx minus 1 comma y minus 1, so that's a shifted version of the input where we've moved the input up by 1 and to the right by 1. So go ahead and take a few seconds to think about these and in your own mind, think about whether you think these are linear systems or they're not linear. So let's take a closer look at these systems. So let's look at this first system. So let's see if the additive property is satisfied for the first system. So we have G is going to give me G plus 10. And I considered another input H, which would give me H plus 10. And if I think of summing the inputs, G plus H, from the definition of the system would give me G plus H plus 10. Now, if the system is linear, then the output should be the sum of these two. So the output, if I sum these two, that should give me G plus H plus 20. And these two things are not equal, so it doesn't satisfy additive property. Okay. Similarly, we can think about multiplying it by, say, some scalar 2g, and in this case the output would be 2g plus 10. And so the question is now basically if this was satisfying the scaling property, then the output should be 2 times g plus 10, because g plus 10 was the output to g itself, and that equals 2g plus 20. And these two things are not equal, so it doesn't satisfy scaling either. So this is not linear. Okay, so let's take a look at this second system, and we want to decide if this one is a linear system or not. So let's imagine an input G, and I get 10G out. I have another input H, and I get 10H out. if I put g plus h in, I would get 10g plus h, which equals 10g plus 10h. And that is equal to the sum of my initial inputs, which is 10g plus 10h. Okay, so these two things give me that. And so these are equal, so that's satisfied. Similarly, if I imagine 2g, I would get 10 times 2g equals 20g. And that is equal to 2 times my original output 10g. And so these two things are equal. And so we do have a linear system. Let's look at this final example. So let's first of all imagine I have some input here, and the value of it is 1. So it's 1 within the hash marked area and 0 everywhere else. And then the system just shifts it up like that. Okay? And it has value of 1. Okay. So now imagine I scale it. So for example, perhaps it's darker. So now it has a value of 2. So I've multiplied my input by 2. The system would simply shift this, and this has a value of 2. And this is simply a scaled version. So if I multiply this by 2, I would get exactly that. And so that satisfies the scaling property. Now we can consider another input. Say another input here, which also has value of 1. And that would be shifted up something like this. Okay. And if I take this, if I sum the inputs, if I sum this and this, I should get something that looks a little bit like this. So here is my input, and so it's where they sum up, it's 2 here, and it's 1 everywhere else. And so this basically would take, my system would take this and just shift it over, like so. Okay, so where this is 1, and this is 2, and this is 1. And this is exactly what I would get if I took this output and added it to this output. If you think about adding up those two things, they would sum up to give me exactly that. And so this satisfies linearity, the additive property, and so this is a linear system.